My name is David Sloan. I work for a company called Idedicom, which is an industry leader in NVMe-based computational storage. I'm here to present the work of Logan Gunthorpe, Stephen Bates, and myself on NoLoad, a stacked file system for NVMe computational storage. Topics today include making a case for compression on high-speed NVMe devices, NoLoad devices themselves. These are our computational storage processors or computational storage drives. Make transparent compression using a computational storage device, stacked file systems, and then NoLoad file system itself. Compression methods used, storage architecture, the interface to NoLoad, as well as some performance metrics. So, making a case for high-speed NVMe devices using compression. NVMe devices provide, or specifically NAND-based devices, provide 1,000 times the performance of hard drives, but are still 5 to 10 times the cost per gigabyte. Introducing high-speed compression before and after reading and writing to these disks can allow us to bridge this gap, putting more data onto this fast persistent memory. Of course, this has to perform very fast, be efficient, and easy to consume. A NoLoad computational storage device is a hardware accelerator behind an NVMe endpoint. Using NVMe as the endpoint allows us to use industry standard drivers, which are CPU efficient and provide high performance interfaces to our underlying accelerators. We have acceleration in compression, encryption, erasure coding, deduplication, as well as compute accelerators and data analytics, video codecs, etc. However, today we will focus primarily on compression as it relates to NoLoad file system. Our computational storage devices can come in two forms, either computational storage processors, where a set of accelerators is exposed through an endpoint to the outside world, or computational storage drives, which have the same configuration where you have computational accelerators behind an NVMe endpoint, as well as flash memory. The computational storage drive allows for internal transfers between computed data and writes to flash, or reads from flash going to a computational accelerator and then back to the PCIe bus. So, transparent compression. Transparent compression is compression that the application is unaware of. This can happen in one of four places, either on the device, as writing a block to a device, compressing it, and then storing it in a different format on the flash, in the block layer, such as Red Hat's Virtual Data Optimizer, in a file system such as ZFS, where data is managed from the read, compression, and then writing to a logical block on the disk, or in a stacked file system, where compression can be injected between the application and a lower file system. Taking a quick step back, a computational storage device used as an accelerator typically requires injecting API library calls into an application. This API will manage all of the calls to the computational storage device and queries to them, as well as any computational storage processor related actions when you're talking between a computational storage device and NVMe storage on a separate device. In order to do transparent computations, things such as compression, encryption, or EC allow for data transforms to then be reverted on the way back to an application. Transparent computations from an application's perspective just need to have data in equal to data out, and do not need to be aware of the format stored on the NVMe device flash itself. Transparent compression, when used on a computational storage device, frees up the CPU to run all of your application code and keeps all of the additional work on a computational storage device before being sent to an NVMe storage. When using non-transparent compression, you need to inject your computational storage processor or computational storage device functions into your application and add your buffer management as well. While this may not add a significant amount of complexity to an application, it does involve modifying existing code bases in order to test out new designs, as well as can lead to maintenance hell when dealing with large public repositories that may have many separate commits that have to constantly get merged with the addition of a computational storage processor into the code base. Ideally, we can pull this out of the application and into the kernel so that every time the application does a system read or write to the underlying file system, the request is first processed with a computational storage device before being sent on to the NVMe storage. This brings us to stacked file systems. Stacked file systems provide a code injection point between the application and the underlying file system. This allows us to extend existing functionality without reinventing the wheel, and gives great interop between existing software stacks, as well as hardware configurations. Some examples of stacked file systems in the Linux kernel are encryptFS, which encrypts data to and from a lower file system, UnionFS, which merges two lower file systems into a single unified mount, and in our work, NoLoadFS, which does compression to an underlying file system. Stacked file systems work by creating a new mount point, where if a file is open here, the example is on mount stacked. This is then some computation is done on this before being passed on to the lower mount, same file name, to the lower file system, which then manages writing directly to disk. In this example, we have an XFS formatted NVMe storage device, which is mounted to /mount lower, and then a higher level NoLoadFS stacked file system, which links mount stacked to lower. When a block of data is written to a file, in this case named A, in the upper file system, it is first processed, compressed, and then stored in a different format to mount lower on the lower file system. When reads and writes take place on the upper file system, data appears as it was written. On the lower file system, you would see the compressed data. Stacked file systems allow for a huge amount of flexibility in system configurations. You can have any lower file system you like for mounting, optimizing for a specific target, as well as additional stacked file systems can be injected before or after NoLoadFS to perform additional useful work. Something such as NFS can be mounted on top of NoLoad file system to share between other computers, or something like encryptFS could even be injected underneath NoLoad file system to encrypt the compressed data. NoLoad file system serves as a manager between computational storage devices and the underlying file system. When I/O requests come in, it manages batching these requests to a computational storage drive or a computational storage processor, which then transforms the data and then writing it to the lower disk. Here we can see a computational storage drive, which contains accelerators and NVMe storage. In this configuration, operations which get fed to the accelerator can then be sent on directly to flash, or vice versa, flash to accelerator back to the host. And a computational storage processor allows for generally larger devices for the acceleration, and then use with a large array of NVMe storage. In order to keep NoLoadFS simple and high performance, we keep as many of the function calls as possible direct pass-through to the lower file system. Things like directory management, file status, and the like are simply passed directly to the lower file system and read as if you were in that. Of course, the read and write operations are the operations of interest that need to be passed on to a computational storage device. And then for per file optimizations or NLFS specific information, we use the built-in X attribute interface in Linux for a existing way of accessing file system specific data. Of course, to make this system easy to use, we have to support file systems which have pre-existing data on them. In order to do this, they're just simply a set of XFS or NLFS X attributes, which are checked. And if they don't exist, the NoLoad file system goes into pass-through mode for that file, where it operates as if it was not in the stack. Of course, this file access is still performed through the NLFS mount point. So moving on to NoLoad file system itself and compression method used. The goal is to use existing infrastructure without reinventing the wheel. So we have software compatible ZLib-Encoding in our hardware compression accelerators. We use a record-based format, which is fixed length records in a lower file system file, maintaining a one-to-one mapping between record position and the position in the file for that data. ZLib-Encoding is compatible with the built-in kernel infrastructure for ZLib compression and decompression. That is, compression can be done either in the kernel using software ZLib or on a computational storage device using NVMe deflate or inflate in our devices. Software recovery is possible using this when there's a hardware failure or system migration, and this allows for asymmetric topologies where only reads or writes are required to be accelerated. Using a NoLoad computational storage processor is a matter of issuing an NVMe read and write command. This, of course, is handled behind the scenes by NoLoad file system. This read and write command are issued in parallel and then are consumed and then written back to simultaneously as the compression core does its work, minimizing the latency of the compression job itself. Once this data has been read back out of the compression core, it can then be passed on to the lower file system for writing to disk. In the case of a computational storage drive, we can push a lot of this functionality into the drive itself. So one single device is responsible for managing the data movement from the compression core's output into the local CMB or peer-to-peer memory, which can then, on the lower file system NVMe write, get pulled out of the internal storage into the internal flash. Keeping all of the NVMe traffic, PCIe traffic to data from the initial data into the compression core and control logic for the second NVMe read and write. So, storage architecture. NLFS uses hole punching to notify the lower file system where data can be omitted. This allows for the lower file system to store files with existing file sizes using existing tools in Linux, but share space on a disk between files of longer lengths. When compressing records, here we have an example of compressing a 1 megabyte record down to a 7 kilobyte compressed data record. Of course, when storing this to the lower file system, our holes need to be aligned to the lower file system block size, so we have to pad up to this block size. This introduces a trade-off between record size and compressibility, as a larger record will have a smaller impact by these block padding segments. When writing uncompressible or low compressibility data, the data can then be thrown out from the decompression core and written raw directly to disk. This allows for higher performance reads, bypassing decompression when it is not required, as well as allows tunability in NoLoadFS when the focus of speed improvements is for high compressible data and partially compressible data is not useful in a given application. NoLoadFS could be tuned as far as saying 50% compressible data isn't interesting, anything higher than that is. Of course, with as much flexibility or granularity as you like there. Compression records. So the NoLoadFS file, here's an example of a NoLoadFS file with 4 records. It has the first 3 in varying level of compression and the final record stored raw. Of course, as mentioned previously, record sizes are fixed length and the raw data record there can be as many mix and match of compressed versus raw records within a file, and it's up to the lower file system how to store this physically on a disk. Holes in a file, of course, get to contain data from other files or a current file as the lower file system chooses. When running NoLoadFS in ODirect mode, we maintain a direct mapping between I/O requests and compression or decompression acceleration jobs. In order to do this, the I/O length is restricted to a record length, as well as position must align with a record in the lower file. This allows for single one-to-one mapping, as well as multiple records in a single I/O, allowing for batching of these requests. Of course, any records which don't align to that get the standard ODirect return of EINVAL for invalid argument. So, NoLoadFS interface. In order to query the compression ratio of NoLoad file system, we use built-in tools. Here we have a list command using the -s argument to give the size on disk as well as the file size. Here you can see a file which we're calling randac, which has been compressed to a file size on disk of 128 kilobytes with its physical size 1 meg. Excuse me. This also works with built-in tools such as stat in C, where the n blocks will give you the number of blocks physically allocated on disk, and the file size will again be the file size expected. When a deeper dive or specific optimizations are required, the X-attribute interface is used. Here you can see that same file, which has been optimized for random access with a small record size of 64K. And then the record stat X-attribute shows the status of every single record within that file. This can be useful for seeing compression distributions within a file, as well as just how this was encoded on disk. Some debug information is provided. Here we can see a global compression ratio. This is the total compression ratio of all data stored to this mount point. The mount ID of 0, first NLFS mount mounted on a system, as well as the lower and upper mount paths. When looking into performance metrics and how a NoLoad file system is being used by the application on top, you can look at the compression record actions, which is the number of times a computational storage device or software ZLib was used to compress or decompress a record. Compression records write and read, as well as raw records write and read, show the total number of times a compressed or raw record was read or written to disk, giving a good indicator of how often NoLoadFS is throwing out compressed jobs. Here we have an example usage of NoLoadFS. We have a XFS formatted drive mounted to /XFS. It contains a pre-populated raw.dat file. This is pre-filled with compressible data. We then mount NoLoadFS on top of this XFS mount point to the NLFS/NLFS mount point using a default record size of 1 megabyte. We then touch sequential.dat and rand.dat data files. This creates 2 new files which will be encoded by NLFS. And we're then going to optimize the rand.dat file for random access using the X-attribute write to NLFS record size, setting it to 64K. Reducing the record size of a file decreases the size of a record that needs to be read from disk, allowing for faster random reads. We can then populate this data and compress it to disk by simply running a copy command between rand.dat and the 2 files, and then call a sync to flush any cache data to disk. ls then shows us the files on disk, and we can see the 2 new files compressed to 128K and 8K respectively, and the raw data remains untouched on the lower file system. Moving on to preference. So performance metrics were gathered using FIO on a NoLoad mount, which was mounted on top of an XFS file system in a 8 NVMe SSD RAID 0 RAID array. I would not recommend RAID 0 for production, but for using minimal hardware for high-speed testing, it's great. This was all run using a NoLoad CSP with a compression and decompression namespace on an AMD EPYC server. Write throughput swept across different compression ratios shows a 8 gigabytes per second, greater than 8 gigabytes per second on all of the larger block size cases, with a small hit on 64K optimized for that random read. In random reads, we can see that we nearly max out the Gen 3x16 link available to our computational storage processor for the higher block sizes. However, on random data, you see a very, very high speed read, as this is coming directly from the 8 NVMe SSD array, as it was not stored compressed to disk. Random writes show a 250 microsecond overhead for compressed data on 256 kilobyte data blocks and 100 microsecond overhead for 64 kilobyte blocks. In random reads, we see a slightly better scenario where we have 100 to 200 microsecond overhead on 256K reads and about 100 to 50 microsecond overhead on 64 kilobyte reads. So, in conclusion, as data volumes explode and NAND gets cheaper, but still not quite as cheap as hard drives, we need hardware acceleration to bridge this gap, pushing more data onto these high-speed devices. NVMe-based computational storage devices allow for high-speed injection of hardware-accelerated transforms into applications. Stacked file systems allow this integration into existing infrastructure and allow you to leverage any optimizations that have been done on this infrastructure. Thank you very much for your time, and I hope you enjoy the rest of this virtual conference.